Okay. All right. And okay. Here we go. All right. So here we are in Math 95. It is 14. And we're going to talk about logarithms today. Um, three main topics. One is what are logarithms? Two are rules of logarithms. And the third is solving word questions with logarithms. All right, so what are logarithms? Logarithms are powers or exponents. Logarithm comes from logos, which means solving. When mathematicians, and actually, even though that's a Greek word, logarithms weren't developed until like the 1700s or something like that. And they were developed to solve math questions that previously were really challenging to solve. The tools that they had to solve them were just very clunky. So I don't remember the mathematician who uh, developed this. I'm sure it was developed in multiple times, but realized if I want to think about powers, exponents, in another way, I can do that using logarithms. So the way I like to introduce it is consider the exponential equation. Three to the fourth equals 81. And so this is just our true equation. Three to the fourth equals 81. And I'm going to break this down into its different pieces. 4 right there. 4 is the power or the exponent. 3 is the base. And 81 is the result. Or the answer, or however you want. So right now I'm just looking at the anatomy of the exponential equation and I'm labeling the different pieces. So far, this is what we did last week. All right, we looked at exponentials and we said, okay, 3 raised to the fourth power equals 81. 4 is a power, 3 is the base, 81 is the result. I'm going to switch this exponential equation, which is in symbol form. I'm going to switch it to a verbal representation. 3 is, start over. 4 is the power that goes on 3 to give 81. The symbols and the verbal tell you the exact same information. 4 is the power that goes on 3 to give 81. Let's do another one. 5 cubed equals 125. So 3 is the power. That goes on what number? 5 to give what number? 125. And you had just written down a logarithm in verbal form. That's the exponential equation in verbal form. That's also the logarithm equation in verbal form. Logarithms are powers. So now I'm going to take this verbal form and I'm going to convert it back to symbols, but I'm going to convert it writing it with a logarithm instead of an exponential. 3, that's the number 3. What's the mathematical symbol we use for is? Equals. 1 plus 1 is 2, right? 1 plus 1 equals 2. Okay, so that is just going to become an equal sign. The power that goes on 5, the power is a logarithm, so I write log for logarithm. Now, if I were creating math, I would just call that power instead of log, but I didn't get to create it. So that's just a word we have to learn and make that association. The base is 5, so it's the power that goes on 5. So I write the 5 down there so I know what the base is. And it gives me 125. That's the logarithm. 3 equals log base 5 of 125. 3 is the power that goes on 5 to give 125. 3 is the power that goes on 5 to give 125. Logarithms are powers. They're a different way of writing an exponential, where instead of focusing on the result, we focus on the power. Take a minute and write this one. Write it as the sentence again. It's the one that maybe you just did because I did notes, but practice. Write it as a verbal sentence and then write it as a logarithm. All right, help me finish this sentence. Blank is the power that goes on blank to give blank.
3 giving.
Hold on, start over. We're going to say it all together. Ready? 4 is the power that goes on 3 to give 81. There we go. Now, if we write that as a logarithm, 4 is, I write the equal sign, the power, I write the log symbol, that grows on 3, so I put 3 down there in the base, to give 81. Often it's written without parentheses, but I like to give it the parentheses to help me remember which is the result that goes in there. There we go. That's how you write a logarithm. That's how you convert from an exponential equation to a logarithm equation and keep all the same information. And whenever I have a worksheet full of this for you, I've been doing this for a long time, I still use this verbal representation to help me, because there's a couple ones that are tricky that I usually get wrong unless maybe I don't write it down, but I definitely say it in my head, right? Because there can be a couple of tricky ones. For example, 7 to the 0 equals 1. How do we write that as a logarithm? Well, the zeros and ones for me are confusing. So it helps if I write it as a sentence first. So 0 is the power that goes on 7 to give 1. And if I can write it that way, then I can match it to my logarithm equation. 0 equals, I write log for the power, that goes on 7 to give 1. If you're tasked with converting from an exponential to a logarithm, and you've practiced this verbal representation, you can do any of them, no matter how complicated. I'm gonna give you a super duper complicated one. (17.32) to the power of negative x squared plus 5x plus 2 equals 3. And I want to write that as a logarithm. So I'm going to write it with the verbal thing first, and I'm going to help myself by actually making the blanks, because the fill in the blanks allows me to kind of take it step by step instead of trying to do it all at once. Blank is the power that goes on blank to give blank. So what's the power in this expression?
3.
No, that's not a power. That's just sitting there. What's the exponent? It's this big mess. But it's still the power. Right? It's a big messy power, but it's still the power. So that means minus x squared plus 5x plus 2 is the power. No, we're not solving it. We're just rewriting it. Yeah, we're just rewriting it as a logarithm. And what does it go on? What's this power going on? Exactly, 17.32, and it gives me 3. And now I can write that as a logarithm, even though it's a super confusing, nasty logarithm, it'll still be a logarithm, and that's my goal. Minus x squared plus 5x plus 2, that one's the power. So is the power, so equals log. And what is it going on? 17.32 to give 3. So we can rewrite any exponential, no matter how nasty, as a logarithm, or vice versa. If you start with the logarithm, you just work up and you can get it to an exponential form. That's my intro to logarithms as, or to what are logarithms. They are powers. And so you can always rewrite an exponential expression as a logarithm expression or vice versa. Okay. Now, logarithms are also functions. What are logarithms? They're powers. They're also functions. They take inputs, they give you outputs. So let's explore the 4 representations of logarithms. What are the 4 representations of mathematical ideas?
Multiplication.
So those are 4 arithmetic operations, but what are the ones I drew in a little picture with the circle and the arrows? Verbal, symbols, graphical or pictures, and tables. Yep.
Symbol with what?
Symbols like formulas, like this would be a symbolic representation.
So you said was a circle, wasn't it?
So I said we've got what? Verbal or words, symbols, or formulas. Oh, I usually write it the other way, but it doesn't matter. And then we got numbers or tables, and graphical or pictures. And then I say you can go from one to the other in a lot of different ways. And the main thing that I want you to work on in this class is every time we talk about mathematical ideas, I want you to practice going from one to the other and vice versa. So in this example, we started with the symbols and we went to verbal, and then we went back to symbols in order to switch the form. Okay. So we're going to look at logarithms using these four different representations. So I'm going to pick a fairly standard, like a kind of a simple logarithm to get started. We're going to look at log base 5. So if I do f of x equals log base 5 of x, these are counting powers of 5. Let's start with the table version here. So here's x log base 5 of x. If x is 5, my output is log base 5 of 5. And that's going to be a very simple number, but let's figure out what that is. Something is the power that goes on 5 to give 5. What power do you put on 5 to get 5? He said it's got 1. Okay, how about 25? You're thinking multiplication, but logarithms aren't multiplication, they're powers. What power goes on 5 to give 25?
2.
2. Blank is the power that goes on 5 to give 25. 2 is a power that goes on 5 to give 25. How about 125? I'll give you a hint. These are going up by 1. What power goes on 5 to give 125? 3, because 5 cubed is 125. Actually, we saw that right here. 5 cubed is 125. So 3 is a power that goes on 5 to give 125. What we're doing with our log function is we're counting powers of 5. If x is 5, 25, 125, the logs are the first power, the second power, the third power. The 1, 2, 3. Logs are powers. I happen to know that 5 to the 4th is 625. So what's log base 5 of 625? 4, because that's the power that goes on 5 to give you 625. We actually have 3 of our representations right here already. We have the formula, f of x equals log base 5 of x. We have the table, and we built the table using our verbal, because again, it helps to talk through it in order to build it out. Now, you can grab calculator. Certain calculators can do this really easily. For those of you watching online, I switched to Desmos, which you're not going to be able to see. We can figure out pretty quickly what's log. To do the base, you do the underscore, which is shift this button, right? Or if you're using a tablet, sometimes there's an option. But log base 5, I'm going to open a parentheses of 125 is 3. All right, so you can get that logarithm pretty easily using some online calculators. Now, a handheld calculator does not have log base 5. Well, that's okay. We can get around that. The best way to get around it is to use Desmos. You can even just ask Google, what's log base 13.4 of 92? I just expected it to tell me, but it wants to use AI, which is dumb. Because it shows me way more than I care about. There it is, 1.74, right? So Google will tell you, it's a calculator. You can use it that way. Desmos is a little, I think, simpler. 15.4, 2, there it is. Okay. The graphical form of a logarithm function let's do log base 5 of x. Every log function goes to the point 1 comma 0 because log base 5 of 1 equals 0. 0 is the power that goes on 5 to give you 1. 0 is the power that goes on 5 to give 1. And then logs come out like this. They walk out toward infinity because if I want bigger x values, I need bigger y values. We look at our table. As x gets bigger, the output also gets bigger, but more and more slowly. And then it actually also comes down like this toward the y-axis, but it never reaches it. That's what a logarithm function looks like. So if I came out here to to 5, I get up to 1. If I came out here to 25, I'd get up to 2. My scale is not perfect. All right. In order to increase your y values, you have to go farther and farther and farther along the x-axis. So let's check in on the symbols just one more time. F of x equals log base 5 of x. When I say, what is f of 125? I am asking, what is the power that goes on 5 to give 125? F of 125, log base 5 of 125. What is the power that goes on 5 to give 125? That's what it means to evaluate a log function, is to find the power. What is the power that goes on 5 to give 125? 3. 3 is the power that goes on 5 to give 125. So f of 125 log base 5 of 125 equals 3. Like I said, there's a lot of content to talk about here. I think this is the most important content, personally, is understanding what logarithms are. Ultimately, they are powers. They allow you to count powers. I think that's easiest to see in a table form. Because here I am just counting my powers. 5 is the first power, 25 is the second power, 125 is the third power, 625 is the fourth power. These log base 5 are counting powers of 5. Now, that doesn't mean, let me make sure my notes are in the right order. That doesn't mean that you always have to count whole number powers. Let's build out our table a little bit more. Still log base 5 of x. Leave a little bit of room at the top. When x was 5, what's the power of 5 I'm looking at right here? When it's just 5. With 1. When x is 25, what's the power I'm looking at right here? What power of 5 gets me to 25? 2. Okay. What about 80? Oh, no. I know what 125 is. What's the power of 5 that gets me to 125? 3. So 80's got to be somewhere between 2 and 3. I don't know exactly what it is though, but I can still put that into my logarithm. There's still a number that powers my 5 up to 80. And for that, we can use Desmos. Log base 5 of 80 is the power that goes on 5 to get me to 80. There is a number, which is 2.72 approximately. Oops. So your outputs of your function, they don't have to be whole numbers. They can be fractional or decimal numbers. 2.72 is the answer because if I take 5 to the 2.72, that's going to be about really close to 80. Get a little closer. All right, that's what it means to say the log base 5 of 80 is 2.72. It means 5 to that power equals 80. We can even do fractions. Well, the world is full of them though.
Yeah.
In the end, most of what we deal with is fractions, because fractions give us a relative understanding, right? You got 20 bucks in your pocket. Awesome. If you're buying a coffee, you're great. If you're buying a car, you're out of luck, right? Because $20 is a big fraction compared to coffee, but a very small fraction compared to cars. So we use them all the time. Log base 5 of 125. Okay, so what is the power that goes on 5 to get or to give 1 over 25? It would be negative because it's a fraction. It's minus 2. Because 5 to the minus 2 is 1 over 5 squared, which is 1 over 25. So you can get negative numbers out of your log. Anytime x is 1, the y is 0. We have that here on our picture. Anytime the x is 1, the y is 0. Logarithms end up being very, very useful. When you move on to take Math 111, that's when you're going to see more applications of logarithms. But the core idea for me is logarithms allow us to count really, really big numbers on our hands. Does anybody know about how big the Fukushima earthquake was in Japan 10-ish years ago? It was like an 8 point something on the Richter scale. So it had like 8 points. I don't know, a couple billion joules of force shaking. We don't have to count a couple billion on our fingers. Boom, 8 on the Richter scale. I can compare that to the Northridge earthquake in California in the 90s, which was like a 5 on the Richter scale. I can start counting really big things just using my hands, which is nice. And that's the key use of logarithm functions, but you'll come back to that in 111. So that is my summary of what logarithms are. There are a set of rules for manipulating logarithms. They're called log rules, but in particular, they're just for manipulating or rewriting logarithms. You can think about it as the grammar. The way we developed a grammar for exponential functions, we also develop a grammar for logarithms. I'm going to write them down. I want you to practice using them. I want you to put them on any note card that you're ever going to use for any math test that involves logarithms, because you'll eventually get them memorized, but there's no rush. The first one is, if I take a log, doesn't matter what base it is, because it doesn't matter, I'm going to get lazy. I'm not going to write a base. And I put two different numbers in there. I put an x times a y inside of a logarithm. I can rewrite that as adding the log of x plus the log of y. Logs split multiplication into addition. That's the first rule. That's actually also something that's super useful about logarithms, because addition is a simpler mathematical operation than multiplication. What if I have the log of, and inside my logarithm, I have x divided by y? I can write that as the log of x minus the log of y. Logs split division into subtraction. The next one is, if I have log of x raised to, and inside that log, I have x raised to some power, I can pull that power down in front as a multiplication. Logs pull powers outside as multiplication. These are our three key rules for rewriting logarithms. And in fact, this is why logarithms were developed, because like I mentioned, in the 1700s or something, or 1600s, mathematicians were doing a lot of calculations that involved complicated multiplication and division and powers. And when you don't have a calculator, that kind of sucks. So the mathematicians who developed logarithms realized, oh, if I have to deal with complicated multiplication, I can logarithm it. And now I just get to deal with complicated addition, which is relatively very easy. So let me just give you an example, and you're going to have some examples on your worksheet. And again, this is, for me, this is practice, checking those rules, following them step by step. Rewrite logarithm of x squared times y cubed over z to the fourth. So I'm going to use the multiplication to addition rule and the division to subtraction rule first to say that log of the quantity x squared times y cubed over 7⁴. I get to split it out into addition and subtraction. Log of x squared plus log of y cubed minus log of z⁴. As a mathematician, a lot of times mathematicians, they say, I don't want to do that. I'm going to do it a different way. And this is an example of that. It's like, I don't want to deal with this multiplication and division. That's dumb. I only want to deal with addition and subtraction. And so they figure out a way to do that. And now I'm going to use the power to multiplication rule to say that log of x squared plus log of y cubed minus log of z⁴ is 2 times the log of x squared, 2 times the log of x, I pull that 2 out in front, plus 3 times the log of y, pull that 3 out in front, minus what?
3 to 4 up front.
Yeah, 4 times the log of z. So those are the rules for rewriting logarithms. As a shorthand, if it's on the top, you add them together. If it's on the bottom, you subtract them off. So I could have a bunch of different terms on the bottom. Each of those terms would be subtracted off. Common mistakes. How to avoid. So avoid common mistakes. Logarithms do not split addition or subtraction. If I want the logarithm of x plus y, this is not equal to the logarithm of x plus the logarithm of y. They don't split addition or subtraction. And each term in the denominator will be subtracted. So if I have log of, let's say, x times y over z times w, that's log x plus log y, since they were multiplied, they split into addition, minus log z minus log w. Each term in the denominator will be subtracted. Okay, couple more. They're technically rules of logarithms. They're more, I like to think of these as they're really examples of logarithms as powers. 7 to the 0 is 1. Great. 19 to the 0 is 1. 1,003,821.76 to the 0 is 1. Okay. Log base b of 1 equals 0, no matter what b is. 0 is the power that goes on b to give you 1. Doesn't matter what b is. So this is the rule. Log base b of 1 always equals 0. And it just comes from the fact that logarithms are powers and anything to the 0 power is 1. How about 8 to the 1? What does that equal? 8. Okay. How about 22 to the first? What does that equal? 22. How about 1.38 to the first? What does that equal? 1.38. So log base b of b equals 1, no matter what b is. That's that rule. Because anything to the first power is itself. Log base 8 of 8 equals 1. Log base 22 of 22 equals 1. Log base 1.38 of 1.38 equals 1. And it's totally fine as your big, because I get this wrong about half the time. I do. I got it right today. The next time I teach it, I'll get it wrong. It's totally fine to check that with a calculator. Right. Okay, I had log base 13 of 1. What does that equal? Wait, is that 13? Is that 1? Is that 0? Just check it with a calculator. That's okay. Because it's easy to get these confused. All right, those are our rules of logs. Moving right ahead. Solving equations with logs. Solve 3 to the x equals 81 for x. So what I'm really asking is, what is the power? Right? Solving for x, I'm asking what is the power? Oh, that's telling me I'm looking for a logarithm. What is the power that goes on 3 to give 81? I can write this as a logarithm, can't I? What is the power? So there's my log that goes on 3 to give 81. And my calculator will tell me that. We've also practiced it a lot. What power goes on 3 to give me 81? 4. Boom. So x equals 4. I should write x here. X equals. Let me rewrite this because I feel like I kind of skipped a step. X is the power that goes on 3 to give 81. I have it written as an exponential first, then I write it as a log. If I don't know what that power is, that's okay. That's what Desmos is for. Let's solve 7 to the x equals 185 for x. So what am I looking for here? I'm looking for power. X is the power, and what is that power going on? 7 to give 185. I have no idea what that number is. Actually, this is the answer. This is the number. This is the number that I'm looking for. This is the power. But I don't know how big it is. Could be in the range of 2, could be in the range of 3, could be in the range of 100. I don't know. So let's get a decimal approximation using Desmos. Easy there. Whoa, hold on. Sorry. log base 7 of 185, about 2.68. And there it is. I found the power. So by understanding that when you're solving an exponential equation, you're looking for the power, that allows you to turn it into a logarithm equation. And then you can use a calculator if you need. But this is the right answer, actually. Log base 7 of 185. That is the number that I'm looking for. I just don't have any intuition about how big that number is. And that's why decimal approximations are nice. Moving right along. I know there's a lot, but remember these are recap lectures, so I go a little bit faster. Let's solve 6 to the x minus 3 equals let's keep it real simple for my brain today. 36. I'm solving this for x. So what am I looking for? I'm looking for power. So x minus 3 is the power. X minus 3 is the equal sign. The power, the log symbol. And what is it? X minus 3 go on? 6 to give me what? 36. Now, if you don't happen to know what that power is, that's what a calculator is for. But 6 to what power is 36? 2. 6 squared is 36. So that must mean that x minus 3 is the power that goes on 6 to be 36. So it is equal to 2. And so now solve for x.
So it was log 6, log 5, each one of them has a specific number, right? Or,
Each,
you know what I mean? A log 6 is a value, log 5 is a value, log 4 is a value, right?
log 6 is a set of instructions.
Okay,
It's the instructions to find the power that gives you that number when it's a power of 6. Log base 5 would say what power of 5 gives you that number. Log base 6 is what power of 6 gives you that number. Log base 8 is what power of 8 gives you that number. So we're looking for the power of 6 that gets you to 36. Well, that's 2, but x minus 3 equals 2, so x must equal 5. And we can check that. 6 to the 5 minus 3, well, that's 6 squared, which is 36. Good. So even if you have something more than just an x in the exponent, you can still use the same process. All right, last example. Let's do 3 times 4 to the x plus 7 equals, hold on, we gotta do a little reverse math here. Yeah, 761. Hey, Gabe. So solve this expression for x. So when you need to solve an exponential expression, but there's more math going on, step 1 is always to isolate the exponential. So if I have 3 times 4 to the x plus 7 equals 761, my first step is to isolate the 4 to the x, isolate the exponential part using math. What do I need to do to isolate the 4 to the x? I have to get rid of the +7 and I have to get rid of the -3. So I get rid of the +7 by subtracting 7 from both sides. And now I have 3 times 4 to the x equals 768. And how do I get rid of the -3? Divide both sides by 3. So we're using our arithmetic skills, right? Our algebra solving skills, but we're using it on the whole exponential term until we get that isolated. 768 divided by 3 is 256. And now I'm looking for x is the power that goes on 4 to give 256. So x is equal to log base 4 of 256. And you stick that into your calculator and you see that 4 is the power that I need. X is 4. Yeah.
Question, that says 761 minus 7 but you go 68.
That's what I was thinking.
Thank you. Bad,
Yeah.
bad arithmetic.
Yep.
-7, so it's not 768, it's 754, I guess. My apologies, and thank you for catching that error. Oh, I know what I did wrong. I made some mistakes in what I wanted to do here. I think I wanted that to be a minus. That's a bummer. Now I've confused you all, possibly. Scratch. Let's start over with new numbers. Like I said, I make mistakes on these things about half the time. Okay, let's try it again. Solve 5 times 3 to the x equals 41. Nope. Oh, goodness. 5 times 3 to the x minus 4 equals 41. Okay. So step 1, isolate the exponential. So if I have 5 times 3 to the x minus 4 equals 41, I'm trying to isolate the 3 to the x. And I'll add, well, first I'm going to add 4, right? I like to SAD map.
Yeah.
And I get 5 times 3 to the x equals 45, right? And then divide both sides by 5. And I get 3 to the x equals 9. So, I mean, 2, right? It may feel comfortable enough to just do that in your head. 3 to the x equals 9. Well, 3 squared equals 9. So x must equal 2. X is the power that goes on 3 to give 9, right? And there are definitely some that are going to be more comfortable than others, right? If I asked, 4 to the x equals 1024, that's probably not something you're going to pull out of your head, and that's okay. So x is the power that goes on 3 to give 9. Well, x is 2. I'm going to talk about one more thing. So thank you for your patience. Which is the natural exponential base and the natural logarithm. So in math, there are special numbers that are so special they get their own names instead of just our numerals, like pi. Right? Pi r squared is the area of the circle, 2 pi r is the circumference of the circle. There's a number in with exponentials and logarithms that is so special, it gets its own letter, which is the letter E. And E is approximately 2.718. So this is called the natural exponential number. E, you can think of it as exponential, but it actually comes from a mathematician, a Swiss mathematician whose name was Euler, E-U-L-E-R, and so it's also called Euler's number. And if we build a function using E as our base, we call this the natural exponential function. F of x equals e to the x. This number is special because it's the number that represents growth that exactly matches size at every point. So the rate of growth, which remember is a percentage of f of x equals e to the x, exactly matches the size of f of x equals e to the x. There's only one number in the universe that does that, and that's the e to the x. Actually, maybe 0 does that as well. Two numbers in the universe that do that, 0 and Euler's number. And that makes it very special because in the end, or in the most simple world, everything grows like e to the x. You can use e to the x as the foundation of any growth formula, any exponential growth formula. It still works the same. E squared is 2.718 times 2.718. E to the ninth is 2.718 times 2.718 times 2.718, etc. And since there's an exponential, there is also a natural logarithm for e to the x. Log base e of x is the power that goes on e to get x. Different places in the world use a different shorthand for log base e. In the United States, we use ln. ln of x is the natural logarithm. And so if you have a scientific calculator, you're going to have log, L-O-G, which defaults to log base 10. And you have ln, which is log base e. So some of your homework questions will ask you to solve an ln. And so you use your ln function. Some of your homework questions might ask you to solve an exponential equation that has an e to the x. So you would use a natural log when you're solving those. All right. I'm gonna stop the recording. Hand out worksheets.